All right, what's going on, everybody? Today we're doing another LeetCode video. This one's called Balanced Binary Tree. So for this problem, we're basically just given a binary tree and we're supposed to determine if it's height balanced. If it is height balanced, we return true. If it's not, we return false. So what is a height balanced tree? Well, we can, basically a height balanced tree is just, if you look at every subnode in the tree, the depths of the left and right subtrees have to, they can't be different by more than one. So if the depths of the left and right subtrees of any node are, greater than one in how they differ, then you have a tree that's not height balanced. So hopefully that makes sense. I'll explain that visually here. So let's just label the levels here to kind of help us. So we have level 0, level 1, level 2, level 3, level 4. So basically, if we were looking at, if we zoomed into, you could either look at this node or the algorithm really when we step through it will break down at this node. But these two nodes have subtrees that are not height balanced. Like this node has subtrees that have different depths, but they're not differing by more than one, right? So the depth of like this left subtree would be 2, and the depth of this right subtree would be 1, but a difference of 1 is okay. It can't be a difference of more than 1. So if we look at this node, right, the depth of this subtree is, we have one node here, another node here, that's 2, that's a depth of 2, or really a depth of 1, but so like that would be the top and this would be the bottom, so really just a depth of 1 there for this node. And then for the left subtree, but the right subtree has a depth of, let's see, it goes all the way down to that 10, right? So, and then this here, the difference between the depths of those subtrees, that's obviously going to be more than 1, right? Because it's 2, this is the difference. So 2 is greater than 1, and therefore, this is not a height balanced binary tree. So let's just go through the whole algorithm with this tree. I'm going to do a depth first search recursively, and we can compare the depth of subtrees basically at every node recursively, and if the depth differs by more than 1, then we'll return -1 recursively, and if that recursive function that we write basically returns a value that's less than 0, because the less than operator is like a little bit faster than other operators. If it's less than 0, nevertheless it'll return -1. If that value is less than 0, the subtrees basically had a difference in height that's greater than 1, so it's not height balanced. But yeah, let's just step through the algorithm. So we're gonna call our recursion on the root node. There's not gonna be any other parameters in our recursive function that we write, just passing in nodes. So we're gonna first pass in the root node, and then we can go, we're gonna first traverse down the left side of the tree, because we're gonna call our recursion on the left child nodes first. So we're gonna call, that's gonna be like the first line of code in our recursive function. So we're gonna keep going until we get to a null tree node. So these little hyphens are like, or dashes are like indicating a null tree node. So we're gonna go this way. Once we get to a null tree node, we're just gonna return 0. So we're gonna return 0 from this function. And then at that point, once we pop back up to this level of our recursion, our code is going to branch it's going to call the recursion on the right child node. So then we would search right. Okay, and we're also going to have some conditions in here that are going to help us check for height balance, but we haven't ran into those yet. So I'll talk about that once we get there. So this will be 0. Notice this is like really similar to finding the depth. I mean, it literally is finding the depth of a binary tree. So it's similar to that depth first search recursive algorithm. So because once we basically have exhausted all of the left and right paths for our recursion, and we get to the very bottom of our recursive function, we're just going to return the whichever depth is greater of the two child nodes, and add 1, basically, to just keep incrementing that depth as we pop back up from our recursion. So we'll have a depth of 1 at this point, right? Because both of these are 0. We take the max of those, so 0, then we add 1. So we get a 1 here. So now we're going to pop back upwards. And at this point, we would go, we would run into that recursive call for the right child node. So we're going to go down this way, but we call it on the left node first, so we have to go this way. We get a 0 because it's null. We pop back up. Now we have to go right. We get another 0. And we pop back up. The max of 2 zeros is 0, and then adding 1 to that, we get 1. Pop back up again, take the max of 1 and 1. It's 1 plus 1 is 2, so the depth here is 2. Notice the depth of all of these subtrees is literally equal, so definitely not greater than 1. So we haven't ran into height imbalance yet. So now we're here. We're going to pop back up to the root node. And at this point, we can start searching right. So we go this way. And then left nodes are always first. So that way, I think it's a pre-order traversal, but it's been a while since I've taken those classes. So come back up this way, and then we would search right. We get a 0, right? Because it's the null leaf node, which technically isn't a leaf node, but just the null tree node there. So we know the parent node is the leaf node. So we pop back up here. Okay, so the max of 0 and 0 is 0 plus 1 is 1. So we have a 1 there. And then popping back up. Okay, so now we have to search right, but we're going to search left now. Notice our algorithm is surely going to break here pretty soon. Not break, but detect an imbalanced tree. So we went that way. We have this 0 here. Okay, so now we're going to pop back up, but we got to search right. So again, we return 0. Okay, now we take the max. That's just 0 plus 1. So we get a 1 there. We're going to pop back up again. Okay, now we have to search right. We're gonna get a 0. Popping back up. We take the max of these. So the max of, and this is still only differing by a distance of, or by a value of 1, right? And that's okay. It's when it's greater than 1. So anyways, we take the max there, which is 1, and we add 1, so we get a 2 here. Okay, so now we're gonna pop back up to this 7. We'll search toward the right, but we gotta go to the left first. Get the 0 here. Pop back up. Okay, now we have to search to the right. Get another 0, and then popping back up. Okay, so the max of 0 and 0 again is just 0, and we add 1. And we're comparing this 2 and this 1 to check for height imbalance, but again, there's just a difference of 1, that's okay. So we'll keep going. We'll take the max of 2 and 1, and that's going to be 2, obviously, and then just adding 1 to that, we get a 3. Okay, but here, now the algorithm is going to break, right? Because we pop back up to this 3, and we're comparing this 1 and this 3, and we see that 3 is, the difference there, because we're just going to subtract and take the absolute value. That's like the quickest, like most elegant way to do that. So 3 minus 1 is 2. Okay, that's greater than 1. So at that point, we're going to just force return a minus 1, pretty much. And at each node, in addition to checking for null pointer, we're also going to check basically if the return value is minus 1. If it's ever minus 1 or less than 0, we know we found a height imbalance. So we can just we don't have to do anything else. We're just going to keep popping back up and returning minus 1, pretty much. So we're going to pop back up this way. We're going to return minus 1. And this function that we called recursively is in our main function is going to be -1. It's going to be less than 0. So we know our tree is height imbalanced. So this is going to be a tree that is not height balanced, right? And for our space and time complexity, we can see for our time complexity that it's going to be big O of n, because we had to visit every node once, right? And every node's null children. So our time complexity is going to scale. It's going to be linear. It's going to be big O of n. It's going to scale linear with respect to our total number of nodes in our tree. And then the space complexity is going to be big O of h for our recursive call stack, where h is the number of nodes, basically just the height of the tree, right? Because we're the way our recursive call stack is going to scale is going to be linear with respect to the height of the binary tree. So it could be big O of n, really technically in the worst case, if the tree was like heavily skewed for the space complexity. But nevertheless, let's just get into the code. So we're going to seed our recursive function. We first need basically a variable to determine, basically to store the return value from our recursive function that we're going to write. So I'll call that function find depth. Actually, it's going to return, we're really only looking for a negative return value, right? So we can, we'll say check is balanced. Okay, and then we'll just seed that root node, and we'll just have some if statements. So if our result is less than 0, if it's a negative value, we can return false. We know that the tree is not height balanced. Otherwise, we can just return true, because if it returns an actual depth, we know that it is height balanced. So let's write that check is balanced function. So I'll make that a private function member. It'll return integer value because it's going to be returning depths, or -1 if we ran into a height imbalance. So we're going to check is balanced. We'll take a tree node, and I'll just call it tn. So the first thing we're going to do is we're going to check if our tree node is null pointer. If our tree node is null pointer, then we can basically just return a depth of 0, right? Because we've reached the null pointer. Basically, that means we're right under a leaf node, so we're going to return a depth of 0. Okay, so after that, we're going to call our function recursively on the left and right tree nodes. So we'll say int, I'll just say depth L here for depth, the left depth, and we'll say check is balanced on the tree node's left child. We want to do the same thing for the right child. So depth right. Okay, and then we want to also check to see if we've reached a height imbalance, right? So we're going to take the absolute value of those and say, so okay, if the absolute value of depth of the left depth minus the right depth, if that's greater than 1, we know we have a height imbalance for sure. So we're going to return -1. Okay, now what if we see -1 during this recursion? Well, we want to just like jump out of the recursion immediately, because there's no point in keep continuing to keep like searching depths further and further with any kind of sophisticated like max or anything like that. Like, it doesn't matter once we find a height imbalance, right? So we want to check first. So we'll say if our depth L is less than 0, right? So if it's -1, we're just going to keep returning -1, right? And we can do the same exact thing after we check the depth for the right subtree, right? So same thing. Okay, and then at the end of this, we actually need to return the depth once we get to the, once we pop back up from all the child nodes and we're like at a node and we need to take the depth and basically pop back up in the recursion. We're gonna do that by taking the max of the subtrees, so depth left and depth right, and then just add 1, right, to whichever subtree was deeper, pretty much, and that's the depth at every node. So this is pretty much it for the code. Let's go ahead and run this. So yeah, hopefully this video helped you understand the problem more. If it did, leave a like and subscribe, and I'll see you guys in the next piece.